dun 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 dun. Let's do another conditional probability example because I know these are hard. These are one of the top 5 hardest things in this class. Let's talk about car alarm. I currently don't have an alarm on my car, but at one point I did own such a car, and if 20,000 strangers, sometimes people I knew, but strangers to the car, touched it, 1 out of those 20,000 we'll say that's going to be a thief. That probably is already high. This is Laramie, okay? So if the thief touches my car, then there's a good chance the alarm's going to go off. And that's what they put on the packages to try to sell these car alarms. That looks impressive. And for not a thief, it's a small chance of it going off. That sounds good. The question is, if you hear a car alarm, what's the chance that it's actually a thief? We're going to do this with 3 different methods. I want to put them side by side, assuming I have room on my board. Let's start with the tree method. For the tree method, I need to figure out which branch it should have first. Now, whether it's a thief or a stranger, that doesn't depend on any other scenario. But whether the car alarm goes off, that does depend on whether we're talking about the thief or just some other stranger. So my first branch needs to be thief or stranger. The probability of a thief is only 1 out of those 20,000. Super small. Probability of a stranger is 19,999 out of 2,000. So big chance there. Now, if it's a thief, the probability of the alarm is 0.999 because it's very likely. That's why we buy the car alarms. If it's not the thief, then the chance of the alarm going off is only 10%. Now, we know the alarm did go off. So this branch, which says it was quiet, that is a branch we're going to burn. This branch here, which says it was quiet, that's a branch we're going to burn. And we want the probability of which branch? The probability of the thief, which is right here. So I'm going to put that probability, which is 0.999 times the 1 over 20,000. 0.999 times 1 over 20,000, that's my numerator. What do I put in the denominator? All the branches that didn't get burned. One of them is going to be the 0.999, 1 over 20,000, same as I have in the numerator. The other one is going to be this branch, which is 10% times the 19,999, I sound like a commercial, over 20,000. I add those up. Make sure that if you put this in your calculator all at once, that denominator is in parentheses. So I take this, divided by that guy, and I get 0.000, I think it was 4999, something like that. So super small chance. This is why when you hear a car alarm, nobody reacts. Let's try the counting method. Let's start with strangers versus thieves. It still looks like thief is misspelled. So I'm going to use a huge number just because I'm trying to avoid decimal places. I think that's 1 billion people. I'm trying to imagine 1 billion people in Laramie. Yeah, that's an ugly sight. So if there was 1 billion people who came to touch my car, then 50,000 of those would be robbers. And there would be 999,950,000 other people not robbers. If you're not trying to steal from me, then I call you a good person. So there's our breakdown. Now, how many of these scenarios would have the alarm? Well, I take this times the 0.999, and I get the 49,950 times that alarm went off so that we could catch the robber. That's good. That's what we want the car alarm to do. There were 50 times that a robber snuck through. You can't design a perfect car alarm. These worry us, but we're just going to have to live with it. Over here with the normal people, there were 99 million times that it went off and was very annoying to the person who's like, Dad, I was just walking past. Most of the time, 899 million times, okay, it was a stranger who was not trying to break into the car and the car stayed silent. Great, that's what we usually hope happens. But return to the question. I know the car alarm went off. What's the chance it's a thief? Can you see why the probability is so small? We're not talking about any of those people. I'm saying, what's the chance it's one of these 49,000 out of the 99 million? And the 49,000 out of all these guys gives us that same probability. When the car alarm usually goes off, it's kind of safe to assume it's probably one of those people. And somebody's annoyed at you. The Bayes method. What the equation says is if you want the probability of something given knowledge about the other thing, say, okay, what's the probability of that something? And then the probability of what was given under that assumption. And then that goes down here in the denominator along with the not A, which is not the piece you want the probability for, but still B because we know B happened under the not A scenario. In our case, what's the probability of a thief? 1 out of 20,000. But we know there was a car alarm, so we multiply it by the probability of a car alarm for a thief. And then in the denominator, what's the probability of a thief? Probability of a car alarm for a thief. And what's the probability of it not being a thief? And then the probability of a car alarm when it's not a thief. And this is a very mathematical approach. If you like that, that's great. Use whatever method works for you. When you get comfortable with all three methods, you actually start to see that it's really the same math. You're doing the same thing three different ways. This equation is the same as this one, except we've multiplied all the numbers by some huge billion. And this is the same as that equation, we just reordered it. So use whatever structure works for you. In the homework, there's even some questions that test whether you've got this by saying, what if there was more than 2 branches? What if we talked about 3 branches? Could you do more? Your goal is to keep at this until it becomes easier than spelling the stupid word thief.